Hello students, welcome back to my channel JP Physics. In last lecture we have discussed about the vertical circular motion of a particle when it is tied to a rigid rod, and another point also we have discussed, it is the maximum speed of the vehicle when it is present at the top of the convex bridge. In this lecture we will discuss next topic of this chapter, that is moment of inertia as an analogous quantity for mass. See, analogy between linear and angular motion I have discussed in first lecture of this rotational dynamics chapter. If you want to clear all that things, you can see that first video of rotational dynamics. See, in that lecture I have told you that is S is equal to R theta, V is equal to R omega, and A is equal to R alpha. All these things we have discussed in that lecture. Now, what is the analogy between moment of inertia and mass? Mass in case of a linear motion and moment of inertia in case of a rotational motion. How it becomes, we will discuss in this lecture. Okay, for that we will consider the rotational motion of a body. When a body is rotating about its own axis, at that time we are going to find out the expression for kinetic energy of rotating body. Very important point of this chapter, that is rotational kinetic energy, or you can say the kinetic energy of a rotating body. What will be the formula for that? We are going to discuss. Let's see how it becomes. If I consider a body is rotating with uniform circular motion, means this body is rotating about its own axis passing through this point O. Any body you can consider, any shape of the body. This is rotating about its own axis with the angular speed omega. Right one, uniform circular motion means omega is not going to change. If I take various particles, that is if I take one particle M1 at distance r1 from this axis of rotation, another particle if I consider m2 at distance r2 from the axis of rotation, and m3 is present at distance r3 from axis of rotation. Okay, now this every particle having its own linear speed, right one. If I consider that speed as v1, v2 and v3, what I can write? V1 is equal to R1 omega, V2 is equal to R2 omega, and V3 is equal to R3 omega, right? Because V is equal to R omega. We have discussed this in first lecture. That is V is equal to R omega, but omega will be constant for this rotating body. For UCM, omega remains constant. Then what will get changed? That is linear velocity for every particle of that mass m1, m2, m3 up to mn. But we have considered here only the three particles. Here not only three particles, not only three masses are present, number of masses will be there. But from that we have considered only 3, 1. We will generalize this equation for n number of particles also. Okay, so V1 will be R1 omega, V2 will be R2 omega, and V3 will be R3 omega. Now we know that kinetic energy for these particles can be taken as Ke1 if I take, then that will be 1/2 m1 v1 square, right? What is the formula for kinetic energy? It is 1/2 mv square. For that first particle, I can write kinetic energy is equal to 1/2 m1 v1 square. Kinetic energy for second particle, I can take as 1/2 m2 v2 square. And for third particle, I will take it as a Ke3, that is 1/2 m3 v3 square. Right? So, if I want the total kinetic energy, that will be the rotational kinetic energy in terms of omega. We can convert that. We can put this value of V1, V2, V3 in terms of omega, and that will be the rotational kinetic energy or kinetic energy of a rotating body. Total kinetic energy of a rotating body. How I can write that? that is kinetic energy rotational. I will write it as a rotational. Okay, kinetic energy, that will be the sum of all these kinetic energy of individual particles. Summation of all these kinetic energies of individual particles. So I will write like this. See, 1/2 m1 in place of v1 square, I will write it will be r1 omega whole square plus 1/2 m2 r2 omega whole square and so on. It is only for 3 particles. I will generalize this for n number of particles, that is total kinetic energy of that rotating body. So here equation will becomes 1/2 m1 r1 square omega plus 1/2 m2 r2 square omega plus and so on up to 1/2 mn rn omega rn square omega square. So if you observe here, 1/2 omega is constant term in each term. Okay, so 1/2 omega will come out from the bracket and it will be m1 r1 square plus m2 r2 square and so on. Okay, see this term I can write like this: 1/2 omega summation mi ri square, where I ranges from 1 to n. The value of I will be ranging from 1 to n. That is 1/2 omega into summation mi ri square. And this new term, summation mi ri square, it is called as moment of inertia. Therefore, 1/2 omega, see here omega square is there, r1 omega whole square, r2 omega whole square means r1 omega square, r1 omega square, r2 omega square, and here also that term will be omega square. Okay, so this formula will become 1/2 omega square into I. That is kinetic energy rotational, that is rotational kinetic energy of this rotating body is given by 1/2 I omega square. 1/2 I omega square. This is the rotational kinetic energy of this rotating body. Rotational kinetic energy. See, in linear motion, what was the formula? It is kinetic energy linear. That was 1/2 mv square, right? In place of mass, in rotational motion, it is moment of inertia, that is I. And here there is a linear velocity. In rotational kinetic energy, there is an angular velocity, that is omega. Means, as the analogous quantity for linear velocity, there is an angular velocity. Analogous quantity for mass, it is moment of inertia. You got this? If we are writing the kinetic energy of a body in linear motion as 1/2 mv square, in case of rotating body, kinetic energy will be 1/2 I omega square. Means this moment of inertia is analogous quantity for mass in case of rotational motion. In linear motion, we are going to consider mass. In case of rotational motion, we will consider moment of inertia. Are you getting this? Means angular velocity, it is analogous quantity for linear velocity. Angular displacement, it is analogous quantity for linear displacement. Angular acceleration for linear acceleration. Similar way, in that similar way, this mass in case of linear motion, then in case of rotational motion, moment of inertia will be there. So by this analogy, you can remember all the formulas analogous to that formulas which are present in linear motion. Linear motion, if you remember all the formulas from linear motion, that is velocity, acceleration, force, torque, and also kinetic energy, power, work done, all the formula you can remember in case of rotational motion if you know the analogous quantities. Now we comes to know first, that is quantity for mass. Analogous quantity for mass in rotational motion, it is moment of inertia. This is new term for you, that is moment of inertia, and it having formula mr square. General formula for moment of inertia, it is mr square. That is, it is a product of mass of the body and square of the distance between that mass and axis of rotation. mr square, moment of inertia having formula mr square. That is, moment of inertia is nothing but product of mass of the body and square of the distance between that mass and axis of rotation. So this is moment of inertia. This is new term for you, and which is analogous quantity for mass in linear motion. If you are taking mass in linear motion, you have to take moment of inertia in case of angular motion, that is rotational motion and also circular motion. You got this derivation? We have done what things we have done here. See, we have considered one rotating body with angular velocity omega. This is axis of rotation about which it is rotating. Then we have considered three masses, that is m1, m2, m3 present at distance r1, r2, r3 from the axis of rotation. Then linear velocity is given by v is equal to r omega. Therefore, we can consider v1 is equal to r1 omega, v2 is equal to r2 omega, and v3 is equal to r3 omega. But kinetic energy of every particle in case of linear motion, see, if this body is rotating, this is the linear velocity, that is straight line. Every time its direction is going to change. This is linear velocity. If you consider simple circular motion, this is the linear velocity, tangential, right? Similar to that, every particle having different linear velocities as v1, v2, v3. But omega is not going to change here. Angular velocity is not going to change here in case of a uniform circular motion. It is a uniform motion. Okay. So, the kinetic energy for that particles will be different. That is 1/2 m1 v1 square, 1/2 m2 v2 square, and all that. If we make the summation of all this kinetic energy, we will get the rotational kinetic energy, or kinetic energy of a rotating body, as the sum of all this kinetic energy, and we are going to write that velocity, linear velocity, in terms of angular velocity, that is r omega. So the formula will becomes 1/2 m1 r1 omega whole square plus 1/2 m2 r2 omega whole square. If we make the calculation, we comes to know about the new term, that is m1 r1 square plus m2 r2 square, and so on. So I have put up that summation. There is a summation of these terms. So shortly, or in short form, what I can write, summation of mi ri square, where I ranges from 1 to n. So this term, summation mi ri square, is nothing but the moment of inertia of that body, and it is represented by symbol I. Okay, so the formula for rotational kinetic energy, it will be 1/2 I omega square. In place of mass in linear motion, in rotational motion, we are going to take it as a I, that is moment of inertia. That is mass, that is moment of inertia, as an analogous quantity for mass, which is used in linear motion. You understood this derivation? If you understood this part, if you like my lecture, please like, share and subscribe my channel, and also press the bell icon so that you will get the notification for next lecture, because in next lecture I am going to consider the next part, that is moment of inertia of a disk and what is mean by the radius of gyration. So thank you.